Hello, everybody. My name is Sandra Vega. I work in the Geosciences Center at UNAM in Mexico. In this presentation, I'm going to talk about a study that we have been doing on the effect of pore structure in thermal conductivity and permeability of volcanic rocks. Let me thank my co-authors, who are also my students, Jonathan and Irving. Volcanic rocks are very interesting porous media due to their great variety of pore structures. A better understanding of the pore structure in volcanic rocks can improve reservoir characterization of these geothermal fields. Permeability and thermal conductivity are transport properties. Permeability can be defined as the ability of the rock to transport fluid. Permeability is a tensor, but in this work, we calculate only permeability in one direction. We use microtomographic images of the rocks. The simulations were done in the commercial software Aviso that uses Navier-Stokes and Darcy's equation. Thermal conductivity can be defined as the ability of the rock to conduct heat. You can see in the figure the distribution of temperature, and this distribution of temperature goes from bottom to top, from lower temperatures to higher temperatures, and the distribution inside of the sample is going to depend on the thermal conductivity point by point in this sample. In this work, we also use tomographic images of the samples and the Aviso software to do the simulations to get thermal conductivity. But in this case, we were able to do it in X, Y, and Z. In this study, we used outcrop samples. We cut it in core blocks of 2.54 centimeters. We acquire images of these core blocks, and we got 26 microns per voxel. That we were able to simulate the thermal conductivity. However, for the permeability, this resolution was not good enough because it didn't resolve completely in a very precise way all the pore structure of the rocks. So we went to higher resolutions, and as you can see here in the figure, we went to physical smaller samples, and these physical smaller samples were captured and acquired different resolutions. So we got that 3 microns per voxel, which were the smaller samples, which are A and B. It was when we could get all the pore structure in all samples. So we got the permeability simulation in this 3 microns per pixel images. And also we did some pore network modeling. In this slide, you can see the photograph of the core blocks of the 7 samples we studied. All the samples come from different locations. However, the andesite M1 and M2 comes from the same location. Actually, it's from the same outcrop sample. But this sample was so heterogeneous that we decided to take 2 core blocks to study its heterogeneity. This is another view of the variety of the samples that we have, and these are cross sections of the tomographic images at 26 microns per pixel. For the thermal conductivity simulation, we not only did the simulations in X, Y, and Z, but we also did it for each division of that we can see on the right image. All these 8 cubes that we divided, we got the simulations in each of them. So we could get the thermal conductivity at each location of the cubes. So we could study how the thermal conductivity varies along whole sample. For the permeability simulation, we did only one direction because these simulations take very long time. So in these simulations, we were able to get the velocity field or velocity field of the fluids. And with that, the actual permeability of each of the samples. Remember, each sample, each core block was cut in 2 subsamples of the 3 microns per pixel. So we have A and B for each core block. We found that thermal conductivity presents some anisotropy in some of the rocks and in some areas of the rock. In this slide, let's concentrate in the middle of the slide where we have thermal conductivity on the vertical axis, on the horizontal axis, the corresponding cubes called 1, 2, 3 to 8. And also we have curves in red, white, in red, green, and blue that corresponds to X, Y, and Z. So you can see for certain cubes, like in the cube number 4 in the Trachai 1, which is the top sample, we have a high anisotropy. So X, Y, and Z changes. And in the andesite, in the middle sample, for the cube A, there is not anisotropy at all. So in this way, we were able to study how the thermal conductivity changes along the whole sample, and also the anisotropy, if there is any anisotropy between at each point or each cube. So these 3 samples that we are seeing here are the 3 extreme cases that we found in all the samples. So we have on the top one, the one that has more fractures and aligned pores. In the middle one, the one that has a lot of aligned pores. In the bottom one, we have the sample that had no preferential orientation of the samples, of the pores. We also did some thermal conductivity versus temperature, and we found there is not much dependence, or there is not a big dependence with temperature. What is leading here is the thermal conductivity of the solid part, and of course the pore space is going to affect, as we saw before, but the actual numbers um, are more, they are led by the thermal conductivity of the minerals constituents of the rocks. So fractures and aligned pores decrease the thermal conductivity. This effect is more notable at the localized areas, and there is a slight effect of temperature on the thermal conductivity at the studied range. For the permeability, let me show you the pore structure, because the pore structure affects a lot the permeability, especially the connected pore space. So here we see 4 of the samples, and this blue color corresponds to the connected pores, and the red ones are the non-connected pores. So interesting to see the, the, the top left sample, which is the one that has more fractures and aligned pores, and the bottom left, the one that has no preferential orientation for the 26 microns per pot cell. However, A and B, we can see some difference. And in the andesite, which is very interesting because it was a very heterogeneous sample, outcrop sample, and then we can see still at the microscopic level, there is a lot of difference. So even the andesite M1 has no connected pores, and the andesite M2, it has more connected pores. Between this andesite M2, A and B, one has a lot of connectivity, giving a very high permeability, which is this subsample B, and the subsample A has some connectivity, but it was not able to get the percolation fully. Let's see this animation that shows the sample, the trash eye one, which is the sample that has more fractures, aligned pores, to see the simulation of the fluid flow in this sample. So remember, the blue ones are the blue color is the connected pores. Here we rotated the coordinated system to visualize better the simulation of the fluid flow that goes exactly from along the whole pore connected structure. So pore structure of the studied samples is very complex, as well as its response of fluid. Although fractures enhance permeability, they might not be the only or the strongest effect in these samples. The found pores are very irregular and difficult to approximate to Euclidean shapes. Regarding the comparison between pore network models and the permeabilities from the images, we see the straight line corresponds to a perfect line where the permeabilities will be equal between the image and the pore network model. So the symbols that are closer to this line, the ones are has a better prediction of the pore network. So we see the diamonds, they have the better, the closer to this line, which correspond to the PNM2, which is the model of the pore network 2, which has the less M pores. So this one was the one that predicted better the simulations of permeability. So in summary, pore structure of the studied samples is very complex, as well as its response to fluid flow. Although fractures enhance permeability, they might not be the only or the strongest effects in these samples, while the found pores are very irregular and difficult to approximate to Euclidean shapes. The pore network model with less dead-end pores seems to emulate better the original pore structure of the studied samples. Fractures and aligned pores decrease the thermal conductivity. This effect is more notable at the localized area, and there is a very slight effect of temperature on the thermal conductivity at the studied range. So we are looking forward to study the effect of scale and resolution for both thermal conductivity and permeability, and to find parameters that better characterize the very complex and irregular pore structure found in these pores. We would like to thank our colleagues that contribute in this work, and our funding source, which is the UNAMPA PIT. Thanks for your attention, and looking forward to meet you in the question section.